You all must have already studied this concept of centroid and moment of inertia. What happens is in the plane, in the problems of say bar, in the problems of bar, our stress was nothing but force by area. So this stress was depending totally upon this area for this applied force of P. If the area was large, the stress induced was less, and if the area was small, for the same force, the stress induced would have been more. So this the amount of stress which was getting developed in case of a bar problem was depending upon A. But say if there is a beam which is subjected to say a transverse load in this direction, and then this beam will bend. Now here the stresses which are developed in the beam are called as bending stresses, and this bending stress, unlike the stress which was getting developed in the bar, does not depend on the cross sectional area of bar directly, but it depends on a quantity called as I, which is nothing but the moment of inertia. So there the stresses developed in the beam totally depends on a quantity called as moment of inertia and not directly on area. So this makes it important for us to understand this concept of moment of inertia. And even before going into this concept of moment of inertia, we will have to look something about the concept called as centroid, right? You all must have already heard a term called as center of gravity, right? Center of gravity. The center of gravity is nothing but a point in a body where the entire weight is concentrated at. Suppose say if I have a body, a general body, then a center of gravity is if I have a general three-dimensional body, the center of gravity is a point where this entire weight is concentrated here at this point. So this is called as the center of gravity. But for a plane of this kind, but for a plane of this kind, we don't call that point as a center of gravity, but for a 2D plane, we call that point as centroid here, right? As a centroid, and this point is denoted by C. And I have placed this plane with this reference axis, that is x and y, and the centroid of this plane is at a distance of x bar from y axis and y bar from x axis. Fine. Now this term this term centroid is geometric geometric center of this plane. This point center is geometric center of this plane. It is nothing but it is a CG, it is a center of gravity for plane bodies which has uniform density. Suppose say if the plane has a uniform density, then we can call this point centroid as a CG of that plane. Fine. Now then what I will do is, here I will consider a small area dA of this entire area A. If this is the entire area, say if this is the entire area A, then I will consider a small area dA on this entire area, which is at a distance of say x from y axis and a distance at say y from x axis. Then the total area can be calculated from this small area just by, as we all know, by integrating it. So the total area can be calculated from this small area just by integrating it. Then I can define now a quantity called as first moment. I can define one new quantity called as first moment, right? you must be knowing a force moment. What is force moment? Force moment is nothing but force multiplied by perpendicular distance is the force moment. Similarly, for area, I can define a first moment as this small area multiplied by the perpendicular distance will be our first moment. And let me denote this the area moment as q. Then with respect to x-axis, I can define this first moment qx with respect to x-axis. With respect to x-axis, I can define this first moment qx as the small area dA multiplied by the perpendicular distance y. And since the area is very small, I will have to integrate it for the entire area. So this is the first moment with respect to x-axis. Similarly, with respect to y-axis, I can define this first moment as integration of this area multiplied by this distance x. The way we had the force moment as force multiplied by perpendicular distance, similarly we have here area moment which will be area multiplied by the perpendicular distance. And with respect to two axes, I get the first moment qx and first moment qy as integral of y dA and integral of x dA. Then this centroid can be determined as follow. So the centroid will be nothing but the first moment divided by area will give us the centroidal distance y bar. So therefore this y bar will be equal to integral of y dA divided by integral of dA. Fine. This area was integral of dA and qx is integral of y dA. So y bar is integral of y dA by dA, where integral of y dA is the first moment with respect to x-axis, and integral of dA is nothing but the total area. So that is how we can locate the centroidal point with respect to x-axis. Now if I want to similarly determine what is y bar, that is the centroidal distance with respect to y-axis, then again it will be qy by a, which can be further written as integral of x dA divided by integral of dA. And then suppose say if I know the properties of this area, if I know the function of this surface of this area, then I can very well substitute it here and I can find the values of x bar and y bar. So just to revise, centroid is a geometric center of the plane, and if the plane is of uniform density, then the point C, which is centroid, matches with that of the center of gravity for this plane, and it can be defined as centroid can be defined as the first moment divided by the area. So centroid will be first moment divided by area, and then there will be, with respect to this axis x and y, there will be two centroids, that is x bar and y bar. X bar is with respect to y axis, y bar is with respect to x axis. Now what we will do is we will look at the different shapes, engineering shapes, which are frequently encountered while solving the problems of beam. Now if you have observed any time, most of the time the cross sections of the beam is I section or the C section or the Z section or say the L section or this L section. Fine. And then in this case we can use some properties of areas to determine the centroid very quickly. Fine. For example, we have this C section, and if we observe this section carefully, this section, this C section is symmetric about x-axis. Since this is our x-axis, this area and this area are exactly symmetric. Fine. Then what will happen here is the first moment about the x-axis, that is area multiplied by y distance, and since it is integral, it will be the sum of this and this. The first moment about the symmetric axis will turn out to be 0. Fine. So here what will happen here in this case, what will happen is, in this case what will happen is the first moment with respect to x-axis, that is integration of y dA, will be 0, because here this side the value will be plus, this side the value will be minus, and then the integral or summation will be equal to 0. Since this is 0, here we get y bar, which is equal to integral of y dA by integral of dA is equal to 0. Therefore y bar is 0. What does this tell us? This tells us that the y bar, that is the, what is y bar again? What is y bar? Y bar is the distance of the centroid from x-axis. So since y bar is 0, that means the centroid will lie on the x-axis itself. I'll repeat again. Y bar is the distance of the centroid from x-axis. Now in this case, since the first moment with respect to x-axis is 0, we get y bar as 0. What does that tell us? It tells us that the CG of the plane lies on the x-axis itself. So here we can learn one important property, that if the area is symmetric about an axis, the centroid must lie on that axis. Let me put down that here. If area is symmetric, about an axis, the must lie on that axis. Very important, because if you can understand this, then we can quickly judge the centroid, the centroid of any section. For example, here this is the I section and our reference axis is situated here, and this I section is symmetric about this x axis as well as this y axis. This I section is symmetric about this x axis as well as this y axis. So the y bar has to be on this axis, and since it is symmetric about y axis, then the x bar should also lie on the y axis. So in that case we can understand that here the x bar is 0, y bar is also 0. That tells us that our CG lies right here. Fine. It is, we could judge this only because it is symmetric about both x axis and y axis. So this first case is nothing but symmetric about an axis, just one axis. This case is of symmetric about both the axes. Now let us see this third case. Right? Now this figure, this section here is neither symmetric about y-axis nor symmetric about x-axis. But if we observe this point carefully, then this point can be called as center of symmetry. This point is called as center of symmetry. What does that mean is, that means this center of symmetry means every line in the area drawn through that point, is symmetric about that point. For example, if I choose this area and if I choose this area, and that is the areas which will pass through a straight line, if I draw through this point, then this area and this area will be symmetric about this point. Fine. So this kind of points are called as center of symmetry. And even here in this case the CG will lie exactly at this point, because this section, although it is not symmetric about the axis, but it is symmetric about this point. It is symmetric about this point, and this point is called a center of symmetry. Fine. So whenever a section is symmetric about an axis, or it is symmetric about a point, the CG will lie on that point. And if the section is symmetric about one axis, then one CG will lie on that point. The second CG with respect to second axis, the second centroidal distance with respect to the second axis, has to be determined. Alright, again I'll repeat this. Since this section is symmetric only about one axis, the one centroidal distance will be 0, that is here the y bar will be 0. So the y bar will be, since the y bar is 0, the CG is sure to lie on this axis. But what about the distance with respect to y? That we need to determine. Further, what we will do is, now we will look at this section which is made up of two triangles, two rectangles. One is this and one is this, and I can call this kind of areas as composite areas. I can call this kind of areas as composite area. Even these areas which we had seen here, these sections, I can divide this as this area, and this as one area, this as one area, and this as one area, wherein I get one rectangle, second rectangle, and third rectangle. Even this is a composite area, and this further I can divide it as first area, then I can divide this as second area, and then I can divide this as third area. Further, again I have this as a composite area. I can divide this as the first area, this as the second area, this as the third area, and so on, in any fashion wherein I can directly know the properties of these areas, right? This becomes straight away, I can use the formula to calculate the area of this first plane, that is this multiplied by this, similarly here and here. Fine. So this kind of shapes, wherein they are made up of the multiple different predefined areas, are called as the composite areas. And let us see how to determine the centroid in the composite areas. Let me again remind you that this L section will be neither symmetric about x-axis, nor it will be symmetric about the y-axis. Fine. Now what is done here is the reference axis, the way here the reference axis for this figure was here, located here, and with respect to this reference axis our plane was placed here. Similarly, this and this sections, our reference axis was here, here the reference axis were here. Here in this problem the reference axis is situated right at the end of this area here. This is the y-axis, and this is the x-axis. This is our x-axis. Fine. And with respect to this axis, now what we will do is we will try to locate the centroid of this area. We will try to locate the centroid of this area. So for this, what we can do is, we know already that the centroid x bar can be found as integral of x dA divided by integral of dA, and y bar can be found as integral of y dA divided by integral of dA. We have already seen this, right? X bar can be found as integral of x dA by integral of dA. Y bar can be found as integral of y dA by integral of dA. But for this kind of composite areas, wherein if I just use if I can just divide this, if I can just divide this here, and if I can call this as first area, and if I can call this as second area, then I can divide this composite area into the discrete areas, wherein I can directly apply the formula of area to calculate the area of this first plane, and I can directly apply the formula of area to calculate the area of this second plane. In that case, what we can do is this integral, I can convert that to the summation. So this x bar here in this composite area can be written as summation of x dA, summation of x x into I can say ai divided by summation of ai, where I goes from 1 to n, where I goes from 1 to n. Summation of, I can write this as xi ai, where I goes from 1 to n. And similarly, I can write this y bar as summation of I equal to 1 to n yi ai divided by summation of I equal to 1 to n ai. So here, since we can divide this composite area into two smaller areas, 1 and 2, or I will go from 1 to 2 because we have only two areas. Fine. So let us see what we get. Now first area 1, A1 can be given as B multiplied by this thickness T. This thickness here is T. This thickness is T. So the area 1 can be written as B multiplied by T. Then we have area 2. The area 2 can be written as, since area 2 starts from this line here, this is the area 2, the total length is C and this is T, so this will become here, this will become from here to here, this will become C minus T because this is T, right? So area 2 can be written as C minus T multiplied by T. This is the area 2, C minus T multiplied by T. Fine. Then I need to find where is x1. Now I need to locate the x1. So x1 is nothing but the distance of this centroid of this area 1 with respect to y, and then by looking at this shape, that is first shape, we know that it is a rectangle, so its centroid should lie exactly at the center of this thickness T. So x1 will be T by 2. Similarly, x2 will be here, this x2 will be here exactly at the center. So this total length is C minus T. So from here to here, it will be half of C minus T, that is C minus T by 2, and then we have this thickness, then it will become plus T. So x2 is nothing but, it is a distance, x2 is a distance right from this center to this. So it is this x2. So this x2 is nothing but T plus C minus T by 2. x2 is C minus T by 2. Similarly, now we will determine what is y1 and y2. What is y1 and y2? y1 is nothing but the centroidal distance of plane 1 with respect to x-axis, and that will be b by 2. and y2 will be the centroidal distance of this plane 2 with respect to x-axis, and that since the thickness is t, it will be t by 2. It will be t by 2. Then to determine this x bar, we have here, if I expand this for this shape, it will be x1 a1 plus x2 a2 divided by a1 plus a2, right? Because our I goes from 1 to up to 2, because we have here only two shapes. So I will be so the summation will be from I equal to 1 to 2, and this will be x1 a1 plus it will be x2 a2 divided by a1 plus a2. So I need to multiply this x1 with respect to a1, so this will be bt square by 2 plus x2 multiplied by a2, so that will be c minus t the whole square, c minus t the whole square multiplied by t c minus t the whole square multiplied by t by 2, and then again multiplying this with this term, I get c minus t multiplied by t square, and this everything needs to be divided by a1 plus a2, that is bt bt plus a2 is c minus t into t, c minus t multiplied by t. So if I further simplify this, I will get this distance x bar, that is the centroidal distance of this shape with respect to x axis. Fine. And similarly I can determine the y bar. As y1 a1 plus y2 a2. If I expand this term, summation of yi ai, where I goes from 1 to 2, it will be y1 a1 plus y2 a2 divided by a1 plus a2, and that will be y1 multiplied by a1, which will be b square t by 2 plus y2 multiplied by a2, that is this term into this term, which gives us c minus t multiplied by t square by 2, and divided by again a1 plus a2, that is bt plus c minus t multiplied by t. And if I further simplify this, I should get this x bar and y bar. Fine. Another easy way of determining all this is just to make one table in this fashion, wherein it starts from serial number, wherein in serial number we will be putting the number of areas, that is area 1. Here we have only two areas, area 1 and area 2. So under serial number I will put it as 1 and 2. Then I will write all the areas, wherein the first area was bt, second area was c minus t multiplied by t, wherein I have written it here. Then I will write the centroidal distance in x direction, that is xi. This is with respect to the y-axis. So centroidal distance in x direction with respect to y-axis is called as xi. So for first shape it was t by 2. And for second shape it was c minus t by 2 plus t, which is written here, and if I simplify this, we can write it as c plus t by 2. Similarly, y1 was the half of this b by 2, and y2 was t by 2. Yes, because this is t, it will be exactly at the center, so it becomes t by 2. Then qx, that is the first moment with respect to x-axis, can be written as b square t by 2, that is area into y. And then For second area, it will become again this area into y, that is c minus t square by 2. Similarly, I can find what is qy, right? That is ai multiplied by xi bar. So it is this term multiplied by this term. Here it was this into this, this into this. Here it is this into this into this. And further, if I add them up, I get the summation of q as follows. If I add this term with this term, I'll get this term. If I add this term with this term, I'll get this term. And this is of course the summation of these areas. And then finally we said that x bar is nothing but summation of ai xi bar divided by summation of a. So this term here, this term, if I write it here, divided by this term will give me x bar, and y bar will be this term here, this term divided by this term will give me y bar. So here, if you follow this tabular method, the chances of doing any mistake, committing any mistake, is very less compared to this. Now since here there were only two shapes, we could very well work out with this method. But when the shapes, when the number of shapes will increase, like in this or this or this, there will be minimum 3 planes, and then there can be 4 planes or 5 planes. In that case, this tabular method will work very easily. Fine. All right. Now we need to slightly take a note of this, that in case if we have a composite areas of such kind wherein we have absence of the area. Now if we can see here, we can look here carefully, that this is the actually the total rectangle ABCD, but from this the rectangle EFGH is missing. Then this can be analyzed either as considering to be a composite area, or what I can say is, or what I can do is, I can directly consider it as this area minus this area, right? And or in this case I cannot analyze this as a composite area, because I cannot divide it in the shapes whose areas will be known to us. If I divide it something like this, then I will have this kind of areas whose area cannot be calculated by a known formula, right? So in this case it won't be possible to go for a composite method like this method. But rather what we can do is, we can handle the absence of the area just by directly subtracting it from this. All right. So what we can do is, the first area, for example in this case, the first area A1 will be if this is say B, if this is say B from here to here, if this is say B and this is say A, I can write the first area as B multiplied by A. Whereas, and if I am considering this to be the second area, the second A2 will be pi by 4, and suppose say this diameter from here to here, suppose say this diameter from here to here is say capital D, then this will be pi by 4 capital D square. And then when we do the summation, it won't be this area 1 plus area 2, but in this case actually it will be area 1 minus area 2, Similarly, this term, the first movement with respect to x-axis and y-axis, when we sum it up, it won't be the addition, but it will be the subtraction of 2 from 1, for this kind of problems. All right. So this is how we can handle the composite areas wherein there is some absence of some areas in between. We need not divide them into small parts, but we can directly consider the whole area minus the smaller area, or first moment of area minus this second moment of area, and we can follow the similar procedure.